Good morning, mathematicians. Oh, what's going on there? Okay. Hi. We're back at it yet again, yet another day. As you can see, I'm not hiking today. But I am going to be drawing pictures of the representations of GL2. So yeah. How exactly will we draw these pictures? Well, I'll tell you. That's the whole point of me being here. My coffee tastes a little weak today. That's problematic. That's an issue. Might have to chug it faster. No hike today, Raj. No hike. Apparently, the skies are crystal clear right now, but apparently it's raining in the mountains. I don't know. Seems sus. I might go for a long jog afterwards, though. Okay. So, as you might recall, so I'm not going to draw a picture of all representations because, what do all representations look like? So, we have, of course, supracuspidal representations. And so these are sort of mysterious ones that can't be probed by induction. And for any supracuspidal, we can take it and we can twist it by a character. And so what do those supracuspidal representations look like? Well, it looks like any complex number. So we twist it by the determinant character to the power of any complex number. But of course, this is periodic in 2 pi I. So I guess we could draw a picture that maybe looks something like this. I guess it's a cylinder. I guess geometrically we would have a cylinder, right? Because these two ends would be identified. An infinite cylinder. But we basically, so of course, like both of these representations are supracuspidal. So we could choose for each class, because then there's also there could be there definitely is supracuspidal representations that say are not an unramified twist of rho. So for each class of supracuspidal representation, we get this infinite tube. We get a whole infinitely many sort of disjoint infinite tubes. You managed to write another short blog post today. Nice. Spectral sequencing. Yeah, okay. Crap, can you remind me your blog post, your blog? Can you reshare the link? I will bookmark it this time. I promise. Can I help you understand de Zagier's one life proof? I have no idea what that is. One line proof of the theorem that P equals A squared plus B squared if and only if. What's the proof? How do I copy message? Oh yeah, there we go. That worked almost. Okay, .github.io. Wait, that wasn't it. Rod. Oh, there we go. Oh, Google remembers. Google remembers, but I better bookmark it. How to deduce mod 4 cohomology from mod 2 cohomology? Well, let's see. Let's look at this other thing. One sentence proof. The number of involutions with a unique fixed point on a finite set. The number of involutions with a unique fixed point on a finite set has the same parity as the total number of involutions. Define a finite set. Define the first involution. Okay, let's understand. The number of involutions with a unique fixed point. The number of involutions with a unique fixed point has the same parity as the total number of involutions. What's the parity of an involution? For the fact that every prime of this form is a sum of two squares. Proof defines an involution on the set, which is easily seen to have exactly one fixed point. It shows that the involution that swaps y and z has a fixed point too, implying the theorem. You believe CSAs are actually applicable for this kind of sum of squares result? Huh. Really? Freaky. The simple proof has always been quite mysterious. Yeah. With the quaternions and the quadratic form there. Yeah. Yeah, my answer, Matthias, is go look up the Stack Exchange post. That's my answer to you. It was a lot to get your head around. Well, there are a whole whack ton of answers on the Stack Exchange post. So I would recommend going and reading those. I'm going to jump over to Arad's blog for a moment here. Computation spectral sequences. Contradicting results. Classic mathematical experience. Am I right? Let's begin with more standard results. This is sort of recipe that allows you to recover Z2 from mod 2 coefficients. Huh? Wow. You need to know of higher Bochsteins. I don't know of higher Bochsteins. The first Bochstein is the usual one. From here, you get a long exact sequence. And the first Bochstein is the connecting homomorphism beta 1. Wait, beta 1. Huh? What? What? Beta 1 squared? I don't understand. Rod, what's going on? Why is it beta 1 squared? I gotta plug in my laptop. Yep. I'm confused. TBH. TBH. Beta 1 is an endomorphism on cohomology mod 2. Oh, I see. Right. I see. Right. Yeah, the codomain and domain do line up. I see. I see. Okay. And we have this nice property. The higher Bochsteins are defined in a similar way as connecting homomorphisms of a more general sequence of coefficients, higher powers of 2. I see. More generally, it smells very p-adic in here. More generally, you can replace this by any other number, typically a prime. As you can see from the long exact sequence, this measures failure of liftability, lifting coefficients, if and only if it's in the image. I'm going to read this more carefully later on my lonesome. But I'm just going to skim the ideas now in the stream. By following this even further, you can construct the Bochstein spectral sequence. Holy moly. The starting page is a mod 2 cohomology. And the differentials in the kth page are precisely the BK. This is fairly highbrow. In which part? You're fine. Not that I mean that it shouldn't be switched, but I didn't even notice. Oh, maybe over where? Over here? I don't know. Okay, the recipe, how to get from Z mod 2 to Z. Every pair of non-zero elements in here and here, connected by the kth Bochstein, contributes to one copy of this inside here. Huh. So you're recovering the, by counting those, you basically get the number of factors of Z mod 2K that show up in here. So you have to play this game again for every prime, I guess, to get all the torsion parts. No, but even then, no, you'd have to play it for every integer, wouldn't you? Or no, wait. What am I? No, I guess the primes would be enough, right? Speaking of spectral sequences, you attended a workshop on Friday related to them. Oh, very cool. This was an in-person workshop? What did you guys learn? How was it? Are there resources you can share for the Maybe the live streams will turn to spectral sequence reading soon. It's funny you say common in algebraic topology to focus on one prime at a time. Because, well, actually, I guess there's a story about a famous Canadian number theorist making fun of my supervisor, saying that he wasn't a number theorist because we fix a prime. I mean, technically, we're not really number theorists. You know, my joke is that I'm legally allowed to call myself a number theorist, even though I do geometry. That's my joke about my research. But every non-zero element not in the image contributes a copy of Z. I see. Nice. That is cool. The recipe gives you a feel for what happens in the Bockstein spectral sequence. The elements Z, as in the second case, are precisely those which represent something non-trivial in the cohomology. And this is precisely how you turn the page. Okay, I need to go do more background reading. But this is cool. Because we don't extract information from the initial page of the sequence, nor from the limiting page, but rather the behavior of the intermediate pages. Your mistake that you made stemmed from trying to extrapolate this recipe to a slightly different one, how to recover mod 4. You falsely assumed that a pair, as in the first case above, connected by the Bockstein map, should just contribute one copy, but that is false. Oh, wait, it's true, but it's not everything. Such a pair will contribute another copy in the lower degree. Cool. Very cool. It was at Klein AT workshop over in Bonn, based on a paper by Antiu. Sorry if I'm butchering that. Well, very cool. Very cool. I want to go to a spectral sequence workshop. But you know, you want to get anything done in this world, you got to do it yourself. So I'll just have to host my own here. And by here, I mean on YouTube. Homotopy theory feels more and more number theoretic the deeper you go. Spaces, spectra, always localized at a prime. Yeah. Well, I went to the Arizona winter school called, it was like interactions between arithmetic and topology. And Jacob Lurie was actually the main speaker there. I couldn't tell you a single thing that happened because I was an undergrad and woefully unprepared for those lectures. But I did get Lurie to sign my copy of Higher Topos Theory that I still have and haven't read. So there's that. I've cracked it open, but décalage? I don't know what that is. And the Bailenson T structure. Oh. To be honest, it was not the place to learn anything about spectral sequences. It was just higher algebra with stable infinity categories. So. One of the 5 greatest under heaven. Who are the other 4, Markov? What's the Bailenson T structure? I feel like I've come across that before. Oh, ha! There's the name of the paper. I've got to change. I'm gonna have to change the name of this office hour. I haven't drawn any pictures of representations yet. That's not true. I drew some pictures. Wow, what a... This paper's crazy. This paper's crazy. It's abstract. This paper explains the theory of spectral sequences. Boom, figure one. Boom, no, nothing out. One sentence abstract. And just boom, here's a table. I mean, go off, King. But that's quite a way to start a paper. Okay, here we go. Here we've got an introduction. We've got an introduction. Still, love it. I mean, I'm here for it. The goal of this paper is to explain the theory of spectral sequences as seen through the lens of the Bailenson T structure. Maybe I haven't seen the Bailenson T structure. I just see a bunch of other things from Bailenson. Every connective cover in the Bailenson T structure is by definition a filtered object. Okay. This is beyond me. Real mathematicians don't need words, only spectral sequences. Yeah. I do love the idea. It would have to be like the right topic, but I do love the idea of giving like a lecture with no words. You know what I mean? Just making like gestures and computations. I feel like there's some sort of math meets performance art piece there. There's also this book, Laws of Form, by George Spencer Brown. I've also thought about like making a YouTube video. The whole book is an E prime apparently, so I guess it doesn't make any. I forget what that means exactly, but it doesn't like make any declarations. It's just like a set of instructions, and you like build up like Boolean logic or something. I don't know. But I thought it'd be cool to do a series where like I just go through the instructions and it's just like a black background and I don't know. Yeah, I don't know. I don't know what I'm trying to say about it. Anywho, let's get back to some math. The correct generalization, boom, we got that. Over here, we got a copy of Z2, and it makes one in the lower one. And the non-zero elements contribute a copy of Z mod 4. Oh, okay. Wait, so there's no free part anymore? I'll have to come back to this nice, easy exercise when we've done more spectral sequence reading together. Okay. So, in order to make the title of this episode not a lie, what do we have here? So, like I said, for each, we could call this, this is maybe called the inertial equivalence class of each supercuspidal representation. We can draw these infinitely tall cylinders. Oh, it's a Z mod 4 module. I see. So Z mod 4 is the free part. Oh, gotcha. Yeah, so we basically get infinitely many infinite cylinders, one for each supercuspidal. And now, actually, I realize I'm going to have some troubles drawing this next picture because, well, so we've talked before about how, well, the representations of GLN come in these pairs of complex numbers. And and we can order them in terms of their real parts. And basically we get one representation for each pair, except when those pairs, except when B is A plus 1. Then we get two representations out of it. And of course, this is also modulo adding integers of 2 pi I, integer multiples of 2 pi I. But maybe as a first approximation to this drawing, we pretend, now these are both complex axes, right? And so we could imagine B is like our Y value. So we're plotting pairs of complex numbers on here, A and B. And we want A to be less than B. So basically, we're looking at everything above this line here. And then what's interesting, and then so we have for this line here, so our region of space is like everything over here, including this solid line. But then we have this other line here, and this is like a double line. So that is like above every point, or no, I guess we could even do a double line construction, like, you know, the point with two origins, right? But take out this line and somehow we glue in a double line to the space. Or we could just imagine it as there's like a second line hovering over it. I don't know what the right way to topologize this would be, but and this is an okay way to the point with two origins. Sorry, is that what I said? The line with two origins. I mean, I guess you could form a point with two origins. Could you? What does that mean even? Isn't that just 2 points? Yeah. So we form this space. The problem is, though, is accounting for this modulo 2 pi I. I'm not sure what the right way to incorporate that would be. Yeah. It's almost like, yeah. It's like somehow these should all be cylinders, right? Or maybe we can put a cylinder, maybe we could think of it as some sort of vector bundle where like, we could make a picture where, well, we have like a product of cylinders, I guess. One is the imaginary part of this, and one is the imaginary part of this. Yo tenacity. So I guess it would be like a product of two infinite. Well, because I mean, we have a whole infinite cylinder of A's to choose from. And then we have a whole infinite cylinder of B's to choose from. So it's like a product of two cylinders. But then we cut that space down. Basically, we cut that space in half because we can assume one of the real numbers is larger. The real part of one is larger than the real part of the other. So yeah, interesting. I mean, I guess we can't. There's no way to visualize this, right? This is like it's 4-dimensional, but interesting. Or I guess, yeah, how else could we maybe visualize it? I guess that's it. Something like that. But now I want to draw a picture. As typical with moduli spaces, the correct approach might be to remove the A less than B restriction and actually take the orbifold quotient with respect to reflection. Or just consider orbits. Yeah. But that doesn't, you did make it, Lockheed, but I'm probably ending stream soon. I am probably ending stream soon. I mean, that's probably, you're right, Arad, that that's probably like the correct thing to do, but does it really give us a nice picture? Guess we're doing orbifolds today. I suppose, in a sense. Yeah. I mean, this kind of gives us like a stack of all irreducible representations of sorts, right? We got our supracuspidal tubes, and then a bunch of other tubes. But I guess, I wonder, like, is the right thing to do is to really view this, as like a vector bundle, or not a vector bundle. I mean, that is a vector bundle, but maybe we want a fiber bundle. Like down here, I wonder, can we refactor it? So what if it was like a torus, right? Because it's like basically, it's basically like an S1 for each of the imaginary parts. But then, right, and then we have like a whole tangent plane of the real values at each part. But then it's like we're taking quotients of the fibers by the relation. It's like, right, it's like a whole copy of this upper half part on each fiber above the torus. I guess that's one way we could think about it. See the memes of natural numbers being replaced by sphere spectrum? Those are supposed to be memes. Yeah, Rod, didn't you know all of higher category theory is just a number theory meme? Yeah. It was just jokes. Okay. So I might end stream there. But I think tomorrow, my plan, now we've got some idea of what these representations look like. Tomorrow, my plan is to go back to Kudla's article and write down the unitary representations and see what those look like in our little pictures here. So I will see you guys tomorrow.